right? So it's going to be a negative 1.5. So it means that the branching, it's going to happen exactly in the middle of these two poles, negative 1.5, right? But how is it going to go out? Is it going to be a straight line going vertically, going this way, going that way? Which way? To find that, we have to look at the angle. So the angle, it's going to be, theta is going to be 2k plus 1 pi divided by the same denominator, 2. Okay? And k can be any value between 0, plus minus 1, plus minus 2, and so on. You only need to put 2 of these numbers because you only have 2 poles, right? So if k is equal to 0, theta is going to be pi over 2. So we know that one of the lines, it's going to be just like this, with this angle, pi over 2. So one of the poles, like move here, goes here, and goes to infinity. That's the other 0, right? The other 0 is infinity. And I'm just gonna put k either equal to 1 or negative 1, doesn't matter. Both of them gives the same value. Let's just like put it equal to negative 1. Then this becomes theta equal to negative pi over 2. So the other line is here. So we have two branches, one like this, the other one like this. Okay, and is our closed loop system stable? Yes, it is stable all the time because the poles, no matter what value you choose for k, it's always going to be on the left hand side. Okay, so this is like how this rule become handy. And the last example I want to do, example 4. Because Dr. Jeff put root locus as part of the syllabus for the course, we have to cover it. It's also like a very useful tool. In many engineering application, you will see that they draw the root locus. MATLAB can automatically draw the root locus for you. But to find the region of stability, root locus is used very frequently. So let's just like look at the very special case like this. Okay, so if I want to draw the poles of this on the S-plane, this is what we have. We have 3 poles, all of them at S equal to 0. 1, 2, 3. All of them here. Okay. Now, do we have any line, any root locus branch here? No, because to the left of it, we don't have any, like only exists to the left of odd number of branches. We don't have any odd number of poles or zeros, sorry. So we don't have any line here, but this is like odd number of poles. So to the left of it, we have root locus branch. Okay, so one of the poles is basically starts like from k equal to 0. One of them goes this way, right? It goes to infinite 0, right? The other one, or basically the other two, we have to again use this formula to calculate like where those asymptotes are and what angle they would have. So let's just like look at sigma, summation of finite poles, that's 0. There's no finite 0, and this is going to be 3 minus 0. So it happens exactly here. So the branching happens exactly here. Okay, and what is the angle of branching? 2k plus 1 pi divided by finite poles minus finite zeros, so 3. If k is equal to 0, this is going to be pi over 3. So like one of the branches goes like this. This is 60 degrees. I can put k equal to 1 or negative 1 here. So like let's just like put negative 1, doesn't matter. Then this is going to become theta equal to negative pi over 3. So the other branch is like this, negative 60 degrees. So one pole moves like this, the other pole moves like this, the other pole moves like this. Okay, as towards infinity. Okay, is this system ever stable? No, because we always have two poles on the right hand side. Okay, as k changes from 0 to infinity, the root Lucas goes to infinity, but two of the poles are always going to be on the right hand side. Okay, so that's the whole thing about root Lucas. It's just like a tool that shows us how the closed loop poles change as this scalar changes from 0 to infinity. So it basically shows the displacement of closed loop poles as the scalar in the closed loop system changes from 0 to infinity. We always only do this like for positive case. Okay, so that's the whole thing about root Lucas. Actually, I think I have one more example, so let's just do one more example. The more the merrier, right? So let's just do one more example. This one, it's gonna be s plus 3, s plus 4, s plus 1, s plus 2. Okay. This is a good example actually. So let's just first locate the poles and zeros. This is one pole, this is another pole, this is a 0. Oh, we already did this one. Sorry, I made a mistake. No, it's not this one. S plus 3 and s plus 4, sorry. Let me actually see here. Imaginary. Sorry, there's one pole here, s equal to negative 1. Another pole, s equal to negative 2. There's a 0 here, negative 3. Another 0 here, negative 4. Okay. We have a line here to the left of odd number of poles or zeros. No line here because there are 2, and one line here. Okay. The root Lucas always starts from the pole and goes to a 0. Okay, so like we know that we are going from here to here, and we are moving towards the zeros. And this one again, it's just like intuitive. You have to do a lot of them to figure this out, but it's